Uh,
Abby.
Okay, I think we'll get started. We can barely see you actually, so even if you're in the front, don't worry. So thank you so much for coming. Sorry we couldn't be there in person. Abby and I together, we will give a talk today about the ocean carbon sink and how we can use CMIP6 models to better understand the ocean carbon sink. And because there's two of us, we can actually introduce each other. So, all right, I will start by introducing Abby. She is from LA in California, but she moved to New York 8 years ago. And her background is actually in physics and astrophysics, even though she is now working as a staff associate in the McKinley Group, where we're working on ocean carbon. And she's been around since last year. She is our group's Python expert, and her middle name is Pam, so I like to call her Python Pam. And she is currently applying to grad school.
Yeah, and a little bit about Thea. Thea is Norwegian. She got her PhD from the University of Oslo 6 years ago in 2018. She used to study geology, so more rocks, mass extinction events, and paleoclimate. And she moved to New York 2 years ago also to join the McKinley Ocean Carbon Group, and she's now also an oceanography researcher. So giving like a bit of background about our entire group, we're led by Dr. Galen McKinley in the middle of that picture. And our whole group's goal is to try to better understand the ocean carbon sink and the ocean carbon cycle in time and space. So we all work with some kind of combination of machine learning, modeling, and observations. And you can find most of us either at LEAP or at Lamont Doherty, a little bit north.
And I can also just mention our beautiful first slide with the ocean was made by Lauren in our group, just so we're giving her a shout out there.
So, why does our group study the ocean? The ocean is what is called a carbon sink. So just like with land, like just how you learn when you're younger about land like trees and plants absorbing CO2 from the atmosphere, the ocean does the exact same thing. So this natural carbon sink will pull carbon from the atmosphere and store it within the ocean. And this concept reduces climate change impacts. So up until now, the ocean has absorbed about 40% of human fossil fuel emissions. And without the ocean absorbing those fossil fuel emissions, the effects we would see of global warming would be far worse than they are now. You can kind of see at the bottom this diagram of like the amount of the gigatons of carbon in the atmosphere without the ocean carbon sink and with the ocean carbon sink over the past several, like 150 years. And this image comes from a website that our group did with a group called Carbon Plan. And the website goes into a lot of really cool detail about the ocean carbon cycle and the ocean carbon sink. And we highly recommend you check it out if you want more detail and more visuals. It's really cool. So throughout the rest of the talk, we're going to talk about a few different concepts and phrases. And so we wanted to go over a little cheat sheet kind of familiar phrases to look for in the talk. And it's totally okay if you don't understand what these mean right off the bat, but just so you're familiar with them when they come up later. And feel free to take a picture if you think that would be helpful. But the ocean sink is the phrase that refers to the uptake of carbon by or in the ocean. PCO2 is the partial pressure of carbon dioxide stored in the surface ocean. It's a way we measure the quantity of CO2 in the ocean. SOCAT is the database online of PCO2 observations globally. A data product is a combination of observations, ocean observations, and machine learning. So basically using machine learning to fill in gaps where we don't have real life observations. A GeoBM is an ocean biogeochemistry numerical model. So this is something that is mainly using things like equations to create a model of the ocean system that's mainly looking into the past. And finally, a testbed, which we'll definitely be talking about later, is a collection of GOBMs, these ocean models or Earth system models, collected kind of all together.
All right, so Abby gave us a very nice overview of why the ocean is important. But one problem with studying the ocean is that the ocean sink is actually very uncertain. And that is why our group and many other people, we work on trying to improve these uncertainties of, or get a better understanding of the global ocean sink. So what we're looking at here is a diagram showing the evolution of the ocean sink, so the uptake of carbon in the ocean since the 1960s, you see this on the x-axis, until about today, or 2022. And on the y-axis, we're looking at the CO2 flux in gigatons. So basically on this diagram, the larger the number, the more uptake of carbon in the ocean. And one thing that we can see is that the evolution here is that we have more uptake of carbon in the ocean since the 1960s until now. So there's an increase in the sink. What we're also looking at here are many different lines, right? We see blue lines, and these represent GOBMs that Abby just mentioned, these ocean models. And then the green lines, they represent data products, so machine learning products estimating the ocean sink. And, two really important observations from this figure. The first one is that all of these different estimates, they show that there is a large spread and a large uncertainty of the ocean sink. Another thing we can look at is if we start looking at the year 2000 and up until today, we're seeing that the two different methods, so shown by the green and the blue lines, they're starting to diverge. They don't agree anymore. So if we're looking at 2022, the green lines, they show a much higher uptake. So the data products show a much higher uptake of carbon in the ocean compared to the GOBMs. And I could also mention that now we're looking at the global ocean sink, and these differences between the different estimates can be even larger in specific regions, for example, in the Southern Ocean. And sort of we're talking about large differences in numbers here, but just to show an example of how big these differences are, if we're looking at the max and min estimate here of the carbon uptake in 2022, we're looking at a difference of 2 gigatons of carbon, which is more than the entire carbon release of the US last year. So it's really important that we reduce these uncertainties, and so we can understand the uptake better. Okay, so why is the ocean sink so uncertain? So there are, several reasons for this, and it's complex, but one very important reason for this is the lack of observations. So for surface ocean PCO2, we can't use satellites and measure everywhere. It's not possible. So the biggest database we have is the SOCAT database. You'll hear this word many times. It is a database of surface ocean PCO2 values collected mostly from ships. And the figure here shows all available PCO2 observations in the SOCAT database since the 80s until today. And what we see here is, we have global coverage if we're thinking about this whole time period, but we also have really large gaps. In fact, the SOCAT database, it covers less than 2% of the global ocean in space and time. And we can also see by the colors here, so darker color means more observations. The observations are highly biased to the northern hemisphere. We have way less observations in the southern hemisphere, and also way less observations during winter months. We can't see that in this figure, but that is also another way this database is biased. Okay, so why is it biased? Why don't we have a lot of observations? There are several reasons. One is sampling is very expensive. Some areas you just cannot measure. It's too dangerous, too harsh conditions, especially in the winter. Some areas of the ocean are covered by ice, so you just can't get there. You can't do measurements. And a lot of these ship measurements in the SOCAT database, they come from commercial ships. So this is going to depend on commercial shipping routes. And most of them will be in the northern hemisphere because there are more people there and more land. And sort of just to really, show how few observations we really have. So now we're looking at all the observations from 1982 to 2022. If we just select 1 year, I think 2022, these are all the surface ocean observations in the SOCAT database we have for a whole year in 2022. Now you're really seeing all the white areas, all the gaps. And let's look at just 1 month of 2022. This is it. So this is a really important reason for why our ocean sink estimates are uncertain.
So there's a few different methods for estimating the ocean carbon sink, which we've kind of covered, but the two main ones are using global ocean biogeochemical models, or GOBMs, like we mentioned before, and the second is machine learning, like observation-based data products. And for the remainder of the talk, we're mainly going to focus on this machine learning method of estimating the sink. So the way that Taya and I specifically use machine learning is to try to use machine learning to reconstruct these PCO2 values everywhere where we don't have data. So on the left, you can kind of see a map of ocean PCO2 where we have observations, and I'll call that the target variable for our machine learning. And everything on the right is what we call feature or driver variables. And these are measurements that we can take in the ocean and also output of a lot of models that we know have, these values have relationships, known relationships to ocean PCO2. It's either temperature, chlorophyll, salinity, mixed layer depth, and the atmospheric concentration of CO2. And so what we're able to do is, we can either get this output from a model, or a lot of this data is able to be gathered via satellite as opposed to by ships. And each of these features will impact PCO2, and our machine learning algorithm will learn the relationships between these variables and ocean PCO2, our target. So to give a bit of a background on very, very basic relationships between some of these variables in PCO2. Let's start with temperature. Temperature can be a proxy for solubility. So there's two kind of main parts of this, which are that cold water is able to hold carbon more easily than warm water, and cold water is denser than warm water. So these two things amount to carbon is brought to the depths of the ocean and farther away from the atmosphere, where the ocean is more cold. And then the second that we'll focus on is chlorophyll. Chlorophyll can be a proxy for biological production. And so the higher the chlorophyll values, the higher this activity, and this high biological activity means that there's more efficient removal of carbon from the surface ocean. So using this machine learning algorithm that we make, we're able to go from something on the left where we have very sparse data. Machine learning can fill in the gaps everywhere in space and time to give us some kind of reconstruction on the right, a full field view of what ocean PCO2 could look like. But a big question is, how do we know if this reconstruction that our machine learning makes is even correct? One way that people typically test their machine learning reconstructions and the machine learning performance is doing something called testing. So 20% of our data set on the left is set aside for testing. So our machine learning algorithm will make this reconstruction, will predict ocean PCO2 everywhere. And at 20% of these spots where we had data, it will go, okay, this is what it should have gotten. This is what the prediction was. Now I will measure the error between these two values. But as you can see on the left, and like we've talked about, there's very little data to begin with. So 20% of very little data is a very small amount of testing that we're able to do.
Okay, so one thing we can do is we can use a testbed. So with using a testbed instead of using actual SOCAT observations, we can look into how well our reconstruction is doing, or how well our machine learning method is doing, and how good our reconstruction is everywhere, and not just only where we have data and then 20% of that. So again, looking on the left here, we're looking at all SOCAT observations in 2021, with lots of gaps. On the right side, we're looking at model output, which we then can call a testbed. And with model output, we have surface ocean PCO2 everywhere because it's a model, right? And a testbed can be model output either from a GOBM or a collection of Earth system models. So when we're talking about testbed, we're talking about model output. So the way we use a testbed is that we then sample the model output, the testbed, based on real-world SOCAT locations. So on this figure, you see these brown tracks. They represent the actual SOCAT observations. Those are the only times and locations of PCO2 that we pull from our testbed. Then we also use driver variables that Abby talked about, but from the testbed. And then we do our machine learning, we reconstruct in the same way, but now the difference is, well, before we could only use, this 20% of test data to look at how well our reconstruction is doing. Now we have a reconstruction that we can compare to the testbed truth everywhere in terms of in time and space. So what we can do now is that we can, compare the truth, testbed truth, to our reconstruction in many different ways and look at different kind of error metrics. Here I'm showing something called bias. So we're looking at whether the reconstruction over or underestimates the PCO2. So the red colors here shows an overestimating of PCO2, so a positive bias, and the green areas show a underestimation of PCO2, so a negative bias. And now, since we're using a testbed, we can look at every single area of the ocean, not just where we have test data. And we can see there are certain regions that are more problematic than others. And also there are certain regions where our reconstruction is actually doing pretty good, where we see biases around 0.
So, related to the testbed, our testbed we specifically made using CMIP6 models. CMIP6 is a collection of Earth system models, and Earth system models are representations of the entire Earth system. So this is ocean, land, and atmosphere. We specifically focus on the ocean component, and all of this model output that we use, and all kinds of model output that we don't use that you could use, is available in the LEAP data catalog. So thank you to the computing team. I know that our testbed specifically will be used in a spring 2025 class, the climate predictions class. So highly recommend taking that class also if you're able. So to give a kind of baby overview of what loading this model output would look like, it would take a code snippet basically just like this. You're able to search the LEAP Pangeo catalog, and you specify the variables you want. So for us, it was chlorophyll, temperature, mixed layer depth, PCO2, salinity, and you specify, oh, I want ocean data monthly, I want these climate scenarios, and then we're able to get what models output the criteria that we need. So after running that chunk of code, we're able to see that 13 Earth system models output the things that we need to create our testbed. You also see those different members, and different members are different representations of the Earth system. So all in all, this is probably over 100 different representations of Earth system models that we can merge into one big testbed. So some applications of making a testbed, some of which we've kind of covered, but we'll get more into. We can look at how sparse sampling can affect our reconstructions, sparse sampling in the ocean. We can also use test beds to kind of examine how future and potential additional sampling in the ocean would affect our reconstructions, maybe sampling in times of the year where we don't typically get data, or in parts of the ocean where we don't typically get data. And we can also look at how our machine learning method and our specific algorithmic design choices can affect our final results. Because it's not just all based on what we feed into the machine learning, it's also based on how we set up the machine learning at the start. But you need to be careful when you are loading any kind of large amount of data or output when you're on Leap Pangeo, because yeah, you have to be careful in where you save the output, and you need to use the cloud storage. Don't save in your Leap Pangeo home directory, or you might mess up people's entire day of work.
All right. Okay, so the last part of this presentation, we are going to talk about 2 case studies. So how we actually use this testbed on Leap Pangeo, why, and sort of some results. So the first case study here, we wanted to look into what happens if we add additional PCO2 values in addition to the SOCAT database, and then observations coming from sail drones. So I don't know if you've seen a sail drone before. You can see it on the photo there, this big orange thing. You can ship this out in the ocean, and it can go and sample in remote areas where you don't go by ship. So it's an autonomous platform you can send out. So by using a testbed before we send out these sail drones, we can sort of check, how many sail drones should we send out, where should we send them, during what month of the year, and how often should we sample, because sail drones are expensive. So by using the testbed to check this, we can save both time and money. So what we did did 2 machine learning reconstructions. So on this side here, on the left side, you see the monthly observations of PCO2 in a 5-year period from 2018 to 2022 from the SOCAT database only. And on the right-hand side, you see a map of the same SOCAT database, but then in addition, we add sail drones in the Southern Ocean in the same time period, so 2018 to 2022. And then we tested 2 different sort of, not patterns, because the pattern is the same, but 2 different strategies. So with one strategy, we sent out 4 sail drones, and then the other one, we pretend to send out 10 sail drones. And then we do our machine learning and see how well we're doing. So, okay, here are some results. So on the left side, so both of these figures are showing reconstruction bias, like I mentioned before. So blue, we're underestimating PCO2. We have a negative reconstruction bias. Red colors, we're overestimating PCO2. We have a positive reconstruction bias. And we're going to just focus in the Southern Ocean where we sent the sail drones, so within that orange box. So on the left-hand side, where we only have SOCAT observations, we see quite a bit of blue, so underestimating of PCO2. And on the right-hand side, where we also have these sail drones, we see a lot more of white color, so we're closer to 0, so less reconstruction bias. So what we can learn from this, maybe not that surprising, but sending out a couple sail drones in the Southern Ocean, we are improving our reconstruction, so we have less reconstruction bias. But we also want to look at how this varies over time. So now we're again looking at reconstruction bias, specifically for the Southern Ocean, but the variation over the years. So if we look at the y-axis here, we have negative reconstruction bias, positive, and then the horizontal line of 0. This is a bit simplified, but let's just think of this as this is the testbed truth. The 0 bias, this is what we're trying to get. So the black line here shows our reconstruction when we have SOCAT observations pulled from the testbed only. So we see an overestimating of PCO2 until about 2018, and then we see, pretty strong underestimating of PCO2. And this is the period where we will add now sail drones. So here we're seeing 2 different sail drone runs, so 2 different reconstructions. The red line here represents 4 sail drones, and the blue line here represents 10 sail drones being added here from 2018 to 2022. What we see is that, all of the reconstructions, they behave similarly, so positive reconstruction bias, until we add the additional sail drone observations. And then we see an improvement in the reconstruction with adding the sail drone. So we're closer to this zero bias than if we're using SOCAT observations only. But another important thing we're learning here is that whether you send out 4 or 10 sail drones, so we're looking at the red versus blue line here, it doesn't seem to matter that much. And sail drones are very expensive. So by using the testbed, we could learn, it's not necessary to send out as many as 10 sail drones, because the improvement you get is it's not worth it, basically, in terms of the cost. So by using a testbed, you can quite easily and quickly assess different sampling strategies. It doesn't have to be sail drones. It could be other things like floats, or just looking into future tracks in the SOCAT database. So yeah, by using a testbed, you can easily assess this. And this is just an example of 3 different publications from our group the last couple of years doing this. And now, this database is, or this testbed is on LeapNGeo. So if anyone wants to work with this, let us know. And if you want to test some other sampling strategies. Okay, so that was the first case study we wanted to talk about. This is the second one, where we're not looking into sampling, but we're looking into sort of the algorithmic design sort of itself and hyperparameter tuning. Okay, so if you're looking at this pie chart, this could be like a typical split of data when you do machine learning. So, 60% of most of it you use for training, then you use 20% or something equivalent to it as your test set, like Abby mentioned earlier, when you're doing your testing to see how well your reconstruction is compared to your truth. But then you can also set aside a 20%, which we call a validation set, that will validate your machine learning model. And basically what you're doing with this sort of set is to see, for example, what kind of combination of hyperparameters in your machine learning model will lead to the best model and lead to the best results. And what we've been doing with the testbed is we've been looking into the validation of the machine learning model. And we were asking ourselves the question of, does it matter which error metric we're choosing for this validation to choose our best machine learning model? And here you just see a screenshot of some error metrics just shown from the scikit-learn machine learning library when you do regressions. And there's a bunch of error metrics you can choose, and you can choose combinations of them. And we just tested a couple to see how this impacts our final reconstruction. So I'm not going to go into super detail. I'm just going to show some examples. This is from a study that our group did in collaboration with Julius that we submitted not too long ago. So we're hoping to get this out, in not too long. But here again, you've seen these types of figures before with the evolution of reconstruction bias. 0 here is what we're trying to aim. We're looking at, if we use negative mean squared error, which is sort of a typical error metric to use, what does our reconstruction bias look like? And we see a high positive bias in the beginning here in the 1980s of our testbed period, and then we see negative bias towards the end. Then we tested to use bias as a hyperparameter error metric. And I know we were talking about bias in 2 different ways here, but it's just another way of looking at our machine learning model. If we use bias instead of negative mean square error, we see some improvements in the beginning. So we see less of a positive bias. And then we also see less of a negative bias in the end. And we're not, adding any more observations. We're not changing anything with our data set. We're only changing the hyperparameter error metric. And then we did some optimization here. Again, come talk to us later if you're interested in specifically what we did, but we did some optimization using bias as a hyperparameter error metric. And we see here we are improving our reconstructions quite a bit, only by switching out this error metric. So this is another example of how you can use a testbed and how it is useful in terms of understanding the ocean sink.
So I think that's about it for our talk, but we highly recommend you check out the webpage that our group made with Carbon Plan. They're on the top right. Our group has a lot of recent work that you can check out on our webpage, or if you have any other questions that you can't ask now, please feel free to reach out to either Taya or I by email. Thank you.
We have time for some questions for anyone in the room. And if you have any questions online, feel free to use the raise hand function or pop your question in the chat.
Hello. I was curious about the sail drones. Like you mentioned several times that they're extremely expensive, and I was just curious, like how expensive are we talking? And then are there like what are the other low cost solutions that you were looking at?
Yeah. I don't want to say a specific number, but I want to say, no, I don't want to say a specific number. I can get you a specific number, but it's very expensive. So you don't want to like you can't send out and they're also, they don't exist. A lot of them don't exist. And actually most of the sail drones are being used by like US military. So yeah, there's a lot of money involved in this. What was your second question? Sorry.
I mean, I was just curious what the other like lower cost opportunities were for getting
Right.
ground truth.
Yeah. Okay. So there are also floats, so biogeochemical floats, and there are quite a few of them, and they're also good in the way that they're autonomous. So you can just send them out, and they're floating around in the ocean, and they're lower cost, I guess, than starting up a new shipping route. The problem with floats is that their uncertainty in their measurement is higher. So they're actually not in the SOCAT database because the way they measure carbon, they don't measure the PCO2 directly, which makes these measurements less accurate. So they're less expensive, but less accurate. So there are like pros and cons to the different sampling strategies here. So that's why using a testbed is, can be very good because then you can test different strategies and yeah, spend less money basically.
Okay, cool. Thanks.
Thank you for your question. This is a good question.
Hi. So can we go back to one of the earlier slide where you have shown the uncertainty of the projection? Maybe the first or the second slide.
Yeah. So this one, right?
Yeah. So I'm curious about where do you see how this current testbed can help narrow the uncertainty we have for projecting this? Like I know the estimation, the estimation by having better data collection, you can narrow the uncertainty around the data product. What about the model projections?
Yeah, so you can't, so maybe we should be more clear on this. Like when using a testbed, like the testbed is not real observations, right? So basically by using the testbed, you can evaluate your method. So, some of these green lines here represent different data products. So you can use the testbed to properly evaluate your method. So let's say, you use the testbed to evaluate this method here and you see that, oh, it's actually doing really good. So then we can, trust this estimate more than other estimates, if that makes sense.
Okay. Hello. Okay. Thanks so much for this talk. I just have a question regarding, I think it's very interesting that you also looked at like the different metrics for your validation set. I have to apologize because I missed a bit the start, how exactly you split into like these different sets. And I just like into the training, the validation and the test set. And I just wanted to know if you also played around with like different kinds of splits, right? Because you can of course split more in a time like in the time dimension, but also in the regional one. And there I just wanted to know if you also analyzed that.
Abby, do you wanna?
I don't think we have played around with that so much, but that's definitely something that we could do in the future. Yeah, we've mainly left the splitting the same for all of our tests so far to be consistent.
Okay. Yeah, quickly just on this, because I know that you had here also at some point a speaker, Lilybell Sweet. I think she's from Leipzig. She gave here some talk. I'm not sure if she talked about this, but she had like a nice paper where she analyzed exactly these questions of how you should do the, like how basically different kinds of splits affect your analysis and what you're looking at, what you're trying to achieve then finally in the test set. Maybe that's something that could be also interesting for your test bed.
Yeah, definitely. We are thinking about that. So that would be a great paper for us to read then.
Thanks.
Thank you both for the talk. I really enjoyed it. My question is about the inputs to your machine learning model and potential biases in between your test bed and what I'm assuming are remote sensing observations. So for example, chlorophyll in the modeled version, are you concerned about, for example, biases in satellite retrievals from like the Southern Ocean as compared to the test bed set?
Well, I guess, or Ted, maybe you seem like you have an answer.
No, I was just so if I understand your question correct, so when we're using the test bed, we're using like everything we're using are model outputs. So we're not using observations at all. So when you know using our machine learning method with real SOCAD and then real driver data, that's one thing. And then with the test bed, we grab everything, all of the variables from the test bed. So
No,
when we're using, sorry.
Oh, is the bulk of your trainings with the test bed, and then you take that trained model and you use it with observations?
No.
Oh.
So what we're, yeah, it's a bit like, you know, tricky because there's a lot of things going on at once. But with in the testbed world, we're just basing it off of observation. So let's see if I have this. Yeah, here. So you know the blue colors here. That's the PCO2 model output in the testbed. So we're just picking for the times of and locations where we have the brown tracks here. We're picking those times and locations, and we're using that in our machine learning. But we never use actual observations when we use the testbed.
Yeah, we're
How well
basically
does-
trying to determine how good the machine learning process that we could apply to actual observations performs, but we're just using model output to do that.
Okay, I see. Thank you.
Hey, yeah, I think these two questions are actually quite related. I was just trying to understand the synergy between the data, the test bed, and the model, but I think it's after hearing the discussion, it's a little bit more clear that you're basically at the end of the day, you want to not have the test bed after the model is like fully trained, and so you're just using the test bed because your data is sparse, but once your model is well trained and well established, which you verified through your test bed, you'll then go straight from the data to the machine learning model. Is that correct?
As into, yeah, and then we would have a data product that we feel more kind of confident in because of the machine learning testing that we did with the test bed.
Okay. Yeah. And so is the machine learning model, would that also producing that data be faster than producing the test bed? Because like the test bed doesn't use the data, it uses physical considerations. But I'm just curious if like, as an end objective, just going straight to the machine learning would be much more faster and efficient than having that test bed intermediate point.
I guess I'm a little unsure of what you mean.
Yeah, sorry. I was just saying, so if you have a test bed that's produced from physical considerations and I guess maybe you're not using the data exactly, but you're extrapolating it somewhere in the data, the main advantage for using the machine learning at the end of the day, instead of having the test bed at all, that intermediate step of the test bed would be because the machine learning technique would be faster for when, in the sense like, in the future you have all the, this data, maybe not all this data, but you have some data, you use the machine learning that would technique that you've trained with the test bed, that would be much faster than producing a new test bed that one could use for as like a full model. Does that make sense?
Yeah. Yeah, I mean the goal of the test bed and the goal of the machine learning is so that we could eventually apply, this machine learning algorithm to real observations,
Yeah.
get a reconstruction that we feel more confident in because we've assessed like how well it performs and how closely it can
Yeah.
get to some kind of reality.
Okay.
Yeah, does that make sense?
Yeah. Okay. I think that makes it more clear. So pretty much, yeah, at the end of the day, the test bed is more of like an intermediate process that you hope to get away from once you've fully trained the ML.
Yeah, and kind of looked at how all of these different machine learning like design choices can affect
Exactly.
the reconstruction, and then getting something like, if we get a reconstruction that's very close to model output, the closest that we can get, then we can feel more confident when we do apply it to real data that the prediction it makes for our actual reality globe looks kind of as close as it can be to reality.
Perfect. That makes a lot of sense. Thank you.
Do we have any other questions that I'm not seeing?
Yeah, I had a related question. Your training in this model world in your test bed, where the resolution is actually quite coarse. And then when you go, you're developing these algorithms that you have confidence in. But when you go to do the observational reconstruction, your observations are effectively point level, point scale. So how are you thinking about the discrepancies in resolution between the two, the test bed and the observations, and how that might affect how you're validating the algorithm or your confidence in its ability to do the reconstruction?
I can comment on this. So in the SOCAD database, it's a gridded product, so 1 by 1 degree, and the test bed is also 1 by 1 degree. So it's
great.
the same resolution. With that being said, it's a very important question you raised, because there are a lot of processes that happen on a much smaller scale that are super important, right? But in terms of comparing to observations, the resolution is the same. We're also actually, it's also on LeapPangeo, is a high resolution testbed. It's 1/10 of a degree with the CSM output, where you can go and look into even smaller scales. Yeah.
Awesome. Thank you.
Hi, Taya and Abby. Great talk. I'm wondering, could you just comment how uncertain is the translation between PCO2 to carbon fluxes? And like, what is the scale of your uncertainties of like tens of micro atmospheres to carbon sink fluxes? Thanks.
Yeah, that's also a very good question. So one thing is when you have your PCO2, but then you also calculate fluxes. You have different wind products. You have, if you want to correct with the river in influx or not, and what is that value? And there are a lot of uncertainties here. And I don't want to give you a specific value because it depends who you ask. But yeah, there are large uncertainties. Let's just put it that way.
Hi, great talk. I wonder at the end of the slides, you talk about reconstruction bias. I wonder, like, at first the bias is positive and at the end it has to be negative.
I'm sorry, I can't hear you.
Yeah, we could at first though.
Is this online or?
Something.
No, the mic ran out of battery.
Oh,
Hi, great talk. I wonder at the end of the slides, you were talking about reconstruction bias, and at first it's positive and it tends to be negative at the end. So I wonder if there's a great reason.
could you?
The reconstruction bias at the end of the talk.
Mhm.
And I didn't totally hear what you said, but something about the at the beginning, the large bias, and at the end, the negative bias. Is that what you said?
Yes.
And then what was the question?
I wonder if there's a particular reason that at first it's positive and at the end it tends to be negative.
Yeah, that is an excellent question. And we're discussing this in this paper that we just submitted with Julius. Our first idea was it has something to do with the SOCAT database, because if you look at the SOCAT database, it has, I don't have a picture or a figure of it now, but it has low observations in the 80s, and then they increase, and you get to 2017, and you have a decrease in observations. So it actually matches this bias. So we're thinking, oh, it has to do with the amount of observations. But then we did a lot of tests with a testbed where we shuffled the SOCAT years. So we would have, way more observations towards the end, or they were like random shufflings. We did this 5-6 times, and we get the same pattern. So what we're looking at there, it has something, we think it has something to do with the fact that atmospheric CO2, it's just increasing. So when you're doing the machine learning, it's not able to understand this increase in CO2. That's not what it's looking for. It's looking for a more normal distribution, and it's not able to properly reconstruct. And in addition to having few observations, if you have more observations, you can try to get rid of this negative bias at the end. And that's also why using bias when you optimize your machine learning method is improving your reconstruction.
Okay. And is the mic working? I think it is. First, Viviana dropped a paper for uncertainty budget, including how the uncertainties in the reconstructed seawater CO2 participate in the global budget. Figure 4 in particular shows the error budget for different locations. I will put this link in the Slack channel, or if you want the link and you're not in our Leap Slack, just let me know and I'll send it over. But I think those are all the questions we have. Taya and Abby, thank you again.
Thank you. Thank you for listening.